Now we're finally moving into the next chapter, talking about a lot of function space coming from a measure space. Okay, so we're going to talk about the LP space, the reduced space, the L infinity space, and the continuous function space. Okay, so they're really important examples of Banach spaces. So if you go on into the next course, the function analysis, you'll see these space and the reduced space a lot. You've probably already seen it if you're taking functional. So let's go through the definition. So everything is really similar to what they did in 450 or even 351 if you talk about the little LP and little L infinity space. So suppose let's fix a measure space. Let's fix some number between 1 and the infinity. So we define the LP space, just the capital L here. So it's all the measurable function where the integral of this function raised to the power p is the integral is less than infinity. So in other words, you can say this is the same as saying f to the raised to the power p is an L1 function. Okay, they're basically the same. And essentially, if p is equal to 1, this is just the L1 function. Okay. Similar to the case in L1, you define this integral, but now if p is greater than 1, you need to raise it to the power of 1 over p. You define it to be the p norm. Okay, so the goal of this video is to prove the p norm is actually a semi-norm. You do something really similar for the infinity case. So you define the L infinity to be, you require, well, now you don't have an integral, but you say the essential support is less than positive infinity. So essential support is essentially the largest value where above this value your function can never be beyond that value on the non-zero measurable set. Okay, so that's the definition. So you take the super of all the t where this function has some value greater than this t on a non-measured zero set. Okay, so that's the essential support. And when this is less than infinity, you say it's an L infinity function, and you do the infinity norm being the essential support. So I'm going to prove the LP space are Banach space. So we first prove this semi-norm and do the quotient as usual. I'll leave the L infinity case on your assignment. They're essentially the same thing, actually a little bit easier sometimes. Anyway, so one thing let's just observe is the following. So these p norm and also infinity norm, they're almost a semi-norm. So first of all, the zero of p norm, that's clearly equal to 0. That's just clear. And if you want to have some scalar times f, and you consider the p norm, so here c is in R, then you can pull out the c by adding absolute value of c, and you multiply the p norm of f. Okay, so these two are really simple. And to show the p norm is actually a semi-norm, you just basically need to show the triangle inequality. So that's the hard part that we need to prove. All right, but yeah, anyways, let's try to prove these inequality. And if you recall what we did in 450, there are two inequality that you need to prove this triangle inequality. So the first one is called the Holder's inequality. If you, again, taken 450, you'll probably remember this. So basically what it's saying is if you pick some p strictly greater than 1 now, and you pick some q so that 1 over p plus 1 over q, it just happens to be equals to 1. Okay, there's a unique q such that this holds. Then you can pick one thing from the LP space. So let's say f is in LP, and you pick another thing is in LQ. And what happens is that if you multiply them, they're actually in L1. And moreover, the 1 norm is bounded above by their the product of the p norm times the q norm. Okay, so you have this inequality. Okay, so the proof is really standard. You need to use some convexity of certain functions. So here's how I do it. So let's prove a little lemma. So suppose you have a and b that's strictly greater than 0. Okay, so then the a times b is going to be less than equals to 1 over p times a to the power p plus 1 over q times b to the power q. Okay, so that's the little lemma. And this lemma, there are many ways of proving it. One thing is you can use the convexity or concave downwards of this logarithm. Okay, so you have the logarithm is concave downward, And if you have two values, let's say x and y, okay, and you can observe because it's concave downward, it just means if you connect these 2 points, the straight line is strictly below the logarithm. And for everything that's inside this interval, you probably already know you can always write it as tx plus 1 over t times y. But here the t is inside the 0, 1 interval. When t is equal to 0, 1, it just corresponds to x or y. And as you can see, if you consider the logarithm evaluate at this value and you compare it with the line between these 2 points, you will have an inequality here. Okay, so let's use some color. So this one is higher than that one. Okay, so what's the red one? So the red one is you evaluate at this t. So the logarithm of tx plus 1 minus ty. Okay, so that's how you evaluate at this point. Is going to be greater than or equals to the value of the combination of these two. So you combine these two using the same t. Okay, so convince yourself this is t times the log of x plus 1 minus t times the log of y. Okay, so for this, because we have this inequality here, so let's let the t is essentially 1 over p here, so 1 minus t is just 1 over q. And what's the x? Well, x is just equals to a to the power p, and y is b to the power q. And you plug in everything, use some basic logarithm, you can prove the inequality. Okay, I'll leave the detail to you for exercise. But anyway, so once we have this, the Holder's inequality is kind of trivial. So suppose I have f and g inside their LP and LQ space. And one thing I can do is that if I go back to Holder, so you can see, because we show the p norm, q norm, and 1 norm, they're both kind of linear. You multiply a positive scalar, you can always pull out the scalar. So we might as well just divide both sides by the p norm of f and the q norm of g. So we can, without loss of generality, assume the p norm of f and the q norm of g are both equal to 1. Well, if they're actually 0, I cannot divide that, but if they're 0, then this inequality is trivial. Okay, so f, for example, if the p norm of f is equal to 0, then f is 0 almost everywhere. Multiply g is still 0 almost everywhere, so everything is just 0. Okay, so let's just say without loss of generality. Okay, so let's do white. Without loss of generality, let's assume the p norm of f equals to 1 equals to the q norm of, q norm of g. Okay. So if I do the integral of f times g, so let's do fx times g of x. So here I have something, let's call it a, and this is b, so I apply the lemma I just proved. This is less than or equals to 1 over p times a to the power p, which is just f to the power p. And then I do the same for g, so 1 over q times the absolute value of g to the power q. And then, as you can see, this is just no other than 1 over p times the f p norm raised to the power p, and the plus 1 over q times the g norm, q of g norm, well, q norm of g to the raised to the power q. And because we normalized f and g first, so these p norm and q norm, they're just equals to 1. Okay, so this is just 1 over p plus 1 over q, which is by assumption is 1. Okay, so this proves the Holder's inequality. And once we have Holder's inequality, let's prove the triangle inequality of this p norm. This is actually just called the Minkowski inequality. So Minkowski. So what it says is essentially the p norm is going to be satisfy the triangle inequality. So let's take f and g is inside LP of mu. Then what we have is the f plus g, the p norm of f plus g, is going to be less than or equals to the p norm of f plus the p norm of g. Okay, so that's Minkowski. So first of all, I need to prove one thing, because I only take f and g in the LP space. The LP space I only define as those functions with a finite p norm. We don't know if it's a vector space yet. Okay, you can scale it. I haven't shown you can add it up. So f plus g, I first of all need to show the p norm actually makes sense, okay? So if I consider the integral of f plus g raised to the power p, well, I basically need to show this is going to be finite, okay? So let's do some really horrible estimation of this. So let's do, because the absolute value of the sum is less than or equal to the sum of the absolute value, so I certainly have that. And each one of them is going to be less than or equals to their maximum, so this less than or equals to twice the maximum, okay? So I can put the twice raised to the power p times the maximum of f, well, raise everything to the power p, so I can just put the power p inside there, okay? And the maximum of these two functions, well, they're both non-negative functions, so I can do a really horrible estimation by just add them up, okay? So let's do f to the p plus g to the p, okay? And then this is clearly less than equals to, because, well, the maximum is always taking one of them, certainly less than equal to their sum, okay? But the goal is right now I can see everything is not is finite here, okay? So here the f raised to the power p, the integral is finite, same for g, and 2 to the p is just some finite scalar outside, so everything is finite, okay? So basically the p norm makes sense. So now if the p norm of the f plus g, so I know it's inside LP, so let's talk about this p norm. If it's equal to 0, then it's just trivial. The left-hand side is 0, right-hand side is non-negative. Okay, so I can just consider the case when it's non-zero. And similar to the case in the Holder's inequality, when the p norm left-hand side is non-zero, I can just divide it by this one norm, and I might as well just assume this p norm is equals to 1. Okay, I can divide the p norm, so I can, without loss of generality, assume that the p norm of f plus g is just equals to 1. Okay, so let's see what happens after that. So now let's consider the p norm of f plus g, which is just f plus g raised to the power p. Okay. So what I can do is I can divide it into two parts, so I can have f plus g, and I do a f plus g raised to the power p minus 1. Okay, so this is what we can do. Okay, so now let's look at two things. So first of all, this is a product of two functions, so let's try to make it into a Holder's inequality. Okay, so I have a p here, so I have 1 plus p, and I need to plus something that makes it equals to 1. Okay, so of course, you have to add a p minus 1 over p, so but you want to write it as 1 over q, so this is 1 over, you flip it over, so this is p over p minus 1, so that's going to be your q, okay? So your q is p divided by p minus 1, okay? And one thing is clear is that this function f plus g raised to the p minus 1 power, that's going to be inside the LQ space, okay? Because f plus g to the whole thing to the p minus 1, and you raise it to q's power, because q is p over p minus 1, so p minus 1 cancel. This is just f plus g whole thing raised to the power p, and you know the integral is finite. Okay, so this is in LQ. What about the other part? Well, the other part, first of all, I can break it using the triangle inequality. So let's just break it into f plus g. So let's do this one. So let's break it into two integrals, f plus g, and I multiply the f plus g whole thing to the p minus 1. Okay, so they are the same. And I have d mu, okay? But either one of them, well, I have this part is in LQ, so this is in LQ. And the first part, the absolute value of f, that's going to be in LP, because f is in LP, so its absolute value is still in LP. And similarly, I have the g part is in LP, okay? So by Holder's inequality, so this is Holder, I have this is less than equals to the p norm of f times what it is, times basically the integral. Let's just write this out, okay? So this is f plus g, the whole thing to the p minus 1, but then I need to do this whole thing to the q norm, okay? And I raise it to the 1 over q, okay? And you do the same thing, you the second one, you also do the holder, so you have a P norm of G, and you multiply the same thing to the 1 over Q again, okay? So this one, we already seen this is just integral of F plus G, the whole thing raised to the power P d mu, which is equals to the F plus G, the P norm to the power P, but we normalize everything, so this is equal to 1, okay? So this is 1, and similarly, the second one, just the same thing, so it's also 1, okay? So this is less than equals to the P norm of F plus the P norm of G, okay? So this is P norm of F plus the P norm of G, okay? So this proves the Minkowski's inequality, and essentially tells you this P norm is a semi-norm, okay? This is the last piece of proving it's a semi-norm.